Known as the icy boundary of our solar system, the Kuiper belt is home to countless frozen objects, from inactive comets to small planetary fragments. Despite its key role in the formation of our cosmic surroundings, scientists have only recently started to demystify this distant region. Surprisingly, it wasn't until 1992 that the Kuiper belt was confirmed as a real, substantial structure encircling the Sun. Even more intriguing is the mounting evidence suggesting that an undiscovered giant planet might still be hiding within this remote expanse. To better understand this far-off region, the James Webb Space Telescope, JWST, has turned its gaze toward the most distant corners of the Kuiper belt. The insights gained have been nothing short of astonishing. New data imply that some Kuiper belt objects, KBOs, might not be as inert as once believed. These bodies could be emitting heat from within, pointing to possible internal activity, and perhaps even conditions that could support basic forms of life. For much of modern astronomy, the region beyond Neptune was largely ignored, presumed to be a simple holding zone for dormant comets that occasionally pass through. But what actually existed past Neptune, whether it was rocky matter, gaseous worlds, or additional planets, remains speculative. The first major theory to address the origin of these distant comets came from Dutch astronomer Jan Hendrik Oort in 1950. He introduced the idea of the Oort cloud, a giant spherical shell of icy material surrounding our solar system. According to Oort, disturbances from nearby stars or interstellar clouds could jar some of these icy fragments loose, sending them inward as long-period comets. This model explained a certain class of comets, but failed to account for short-period ones like Halley's Comet. In 1951, astronomer Gerard Kuiper proposed a complementary theory to fill this gap. He suggested the existence of a flat, disk-like zone of icy debris just past Neptune, a region that would later bear his name. Although his hypothesis made sense, there was no proof for decades because telescopes lacked the capability to observe such distant, faint bodies. That changed in 1992, when Jane Liu and David Jewett, observing from Hawaii's Mauna Kea, identified a dim, slow-moving object that turned out to be the first verified trans-Neptunian object, TNO, eventually named 15760 Albion. This marked the official discovery of the Kuiper belt and brought Kuiper's earlier theory into scientific reality. With the region's presence now undeniable, astronomers began studying its features in more depth. The Kuiper belt spans a vast, flattened ring-shaped area between 30 and 50 astronomical units, AU, from the Sun. 1 AU is the distance from the Earth to the Sun, roughly 150 million kilometers, placing the belt between 4.5 to 7.5 billion kilometers out. At its outer edge, this disk merges into the beginning of the even more expansive Oort cloud. When compared to the asteroid belt between Mars and Jupiter, the Kuiper belt is 20 times wider and holds up to 200 times more material. There are likely more than 70,000 sizable objects in this region, each over 100 kilometers in diameter, but many smaller ones remain out of reach for even advanced telescopes like Hubble. Despite the limitations in detecting the smaller members of this cosmic family, science has made important strides. In 2019, researchers spotted a Kuiper belt object just 1.6 kilometers in size, offering tangible proof that the belt contains not only large, but also tiny bodies. Still, scientists have only scratched the surface of understanding the belt's total makeup and diversity. One of the Kuiper belt's biggest impacts has been its influence on how we define planets. In the early 2000s, the discovery of other Pluto-like bodies, such as Haumea, Makemake, and Eris, forced a re-examination of what qualified as a planet. The International Astronomical Union, IU, responded in 2006 by redefining the term planet, stripping Pluto of that status and designating it a dwarf planet. The term Plutoid was created to describe these distant icy worlds. Even as Pluto was reclassified, a new theory began to gain support, that an unseen, massive planet might exist beyond Pluto. In 2015, researchers noticed unusual patterns in the orbits of 6 large trans-Neptunian objects, including Sedna and 2012 EP-113. Their orbits were elongated, similarly angled, and shared a peculiar orbital plane tilted roughly 30 degrees from the ecliptic. This consistency hinted at a gravitational force at work. The idea of Planet 9 was formally proposed by Caltech astronomers Mike Brown and Konstantin Batygin. Their detailed computer simulations showed that the strange orbits of these distant objects could be explained by the gravitational pull of a massive, distant planet. Statistically, the odds of these orbital alignments happening by random chance were less than 1%. Other theories were also evaluated. Could the collective gravity of the Kuiper belt's known objects cause such patterns? Calculations showed this was unlikely. The belt would have to be at least 100 times more massive. Another possibility involved an unseen disk of fine debris, but infrared observations ruled out this scenario based on the absence of expected light scattering. This left Planet 9 as the most plausible explanation. Models suggest it could be similar to an ice giant, about 10 times the mass of Earth and somewhat smaller in diameter than Neptune. It would follow a highly elliptical orbit stretching anywhere from 400 to 800 Australian dollars, with its furthest point potentially even farther out. The planet's orbit would be so long, between 10,000 and 20,000 Earth years, that it might currently be near its aphelion, the point furthest from the Sun. This, along with its low brightness and minimal sunlight reflection, would make it nearly invisible in optical surveys. Infrared telescopes like JWST are better suited for spotting the faint heat signatures it might give off. Brown and Batygin estimate a 90% or higher likelihood that Planet 9 exists. The combination of its distant orbit, low light emission, and estimated temperature, around 47 K or minus 226 degrees Celsius, makes it one of the most difficult objects to detect. In visible light, its brightness might be only 0.006, less than that of Neptune, making infrared detection the more viable option. Finding Planet 9 would be a groundbreaking milestone, not just because it would return the count of major planets to 9, but because it would reshape our understanding of the solar system's structure and evolution. It would suggest a more chaotic early solar system in which gravitational interactions flung planets to the edge of the Sun's influence. While that search proceeds, JWST has already revealed another exciting find, not a planet, but signs of heat activity in dwarf planets like Eris and Makemake. Research led by Christopher Glane at the Southwest Research Institute analyzed spectral data and detected methane ice that appears to have undergone thermal transformation. This implies that recent warming events occurred beneath their surfaces. Such internal warmth could stem from radioactive decay or tidal forces, much like the processes that keep Earth's core hot. If confirmed, these heat sources could drive subsurface changes or even allow liquids or gases to move through icy shells. On Earth, such conditions are critical for life. If liquid reservoirs are confirmed, perhaps mixtures of water and ammonia or salty brines, the idea of habitability becomes plausible, even on these remote, frozen landscapes. Microbial life could theoretically exist where warmth, water, and organic compounds intersect. Therefore, the Kuiper Belt is far more than a frozen junkyard. It is a region teeming with scientific potential, a place to explore planetary evolution, habitability, and the fundamental makeup of our solar neighborhood. The range of objects here, from large icy bodies to tiny fragments, offers an exceptional laboratory for cosmic research. One could compare the Kuiper Belt to a galactic Rosetta Stone, capable of unlocking mysteries about the origins of planets, the behavior of remote celestial bodies, and the unseen dynamics shaping our solar system. Whether it's through finding Planet 9, studying cryovolcanism, or expanding our inventory of KBOs, every new insight alters our understanding of the cosmos. Efforts to locate Planet 9 continue across multiple observational platforms. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSSD, will soon scan the sky in unprecedented detail. Space-based infrared telescopes and focused JWST campaigns are also targeting likely regions where this elusive planet might be hiding. Meanwhile, missions such as New Horizons, which flew past Pluto and continues to explore trans-Neptunian objects, provide valuable data. Future proposals include an interstellar probe that could directly explore the Kuiper Belt and even the Oort cloud, aiming to resolve some of astronomy's most pressing questions. As the summer of 2025 advances, Researchers are combing through vast datasets from past sky surveys while preparing new observation schedules. The goal? To catch a glimpse of Planet 9. Even a single confirmed image with verifiable movement would forever alter planetary science. But whether or not Planet 9 is found, the Kuiper Belt remains a beacon of astronomical curiosity. Its icy members are relics of the solar system's youth, potentially preserving chemical signatures from billions of years ago. Studying its shape and behavior gives us clues about how giant planets migrated during the solar system's formative years. The Kuiper Belt structure, including mass distribution, resonant object populations, and the scattered disk, provides a testing ground for models such as the NICE model, which describes early planetary migration. These theories help us understand how current planetary arrangements came to be. Furthermore, this outer zone is an ideal laboratory for studying chemical evolution. If internal heat is common and organic compounds are present, then even such distant worlds might support prebiotic chemistry. The discovery of such molecules would suggest that the conditions for life might be more widespread than previously assumed. In addition, studying the Kuiper Belt can reveal information about the solar system's interactions with the Milky Way. Stellar flybys from ancient times may have disturbed the belt's outer edge, influencing the orbits of objects like Sedna. These changes serve as a record of our system's journey through the galaxy. Ultimately, the Kuiper Belt is far more than a distant boundary marking the edge of our known solar system. It is a vibrant and dynamic arena filled with mystery, potential, and discovery. Once dismissed as a simple reservoir of icy debris, this sprawling region has proven to be a cosmic treasure trove, holding countless clues about the formation and evolution of the planets, moons, and other celestial bodies we observe today. Its inhabitants, ranging from tiny icy fragments to dwarf planets like Pluto, Eris, and Makemake, are relics from the early solar system, preserved in their frozen orbits for billions of years. They act as time capsules, offering insights into the materials and conditions that existed when our solar system was just beginning to form. The Kuiper Belt may also conceal entirely new worlds, possibly including the elusive and still unconfirmed Planet 9, whose gravitational influence could explain strange orbital patterns observed among distant trans-Neptunian objects. Beneath the icy crusts of some of these bodies, hidden subsurface oceans might exist, fueled by internal heat sources like radioactive decay or tidal flexing. If such oceans are confirmed, they could even offer environments suitable for microbial life. Geologically, the Kuiper Belt challenges long-held assumptions by revealing unexpected levels of activity, such as cryovolcanism and resurfacing. Each new finding reshapes our understanding of what is possible in the far reaches of space. As our technology and telescopes grow more powerful, the Kuiper Belt continues to propel human curiosity forward, unlocking the solar system's most ancient and guarded secrets. The next decade may unlock even greater revelations. Imaging Planet 9, observing geysers or cryovolcanoes on distant bodies, or sending spacecraft to explore these icy remnants up close. Such milestones would open a new era in planetary science, one that fully appreciates the Kuiper Belt not as an afterthought, but as a key chapter in the story of our solar system.